So we're going to talk about mostly stuff from Chapter 9, and hopefully this will help you with your homework a little bit. So let's start with subspaces. So when we're talking of subspaces, the first thing we do is we want to define a set or a subset. And in this case, we define a subset on Rn and we call it V. Then from this subset, how do we know if V is a subspace? Well, V is a subspace if it is closed under linear combination, which means that if there's any element in V, V1 and V2, and I take a linear combination of it, which means scalar multiplied by a vector and the vector sum, and then when you combine the two conditions, you can say alpha 1 V1 plus beta, alpha V2 plus beta V2. If this new element, let's say V3, lies in V, then you can say that V is indeed closed under linear combinations. And if V is closed under linear combinations, then V is a subspace. So if you know that, let's see how to apply something like that. So in this case, let's say I've given you a set V that is a subset of R2. So it has two elements, x1 and x2. And the elements are such that they satisfy this condition x1 squared plus x2 squared is 2x1, x2, given x1 and x2 lie in the set of real numbers. So the way to solve that would be, let's simplify this condition first. And if you look at it, it's easy to see it's like x1 squared plus x2 squared is 2x1, x2. So what it's basically trying to say is x1, if I take the terms on the left-hand side, becomes this, and then we know that this is just x1 minus x2 whole square is 0, which means x1 is x2. So basically, this definition of V, we can rewrite it as V is a subset of R2 such that each element in V is the same, and then X belongs to R. So now that we've simplified it, we can say, now we need to check if V is indeed a subspace. Now, an easy way to do it will be to check if the 0 element belongs in V. So check 1, you want to check if the 0, 0 belongs in V. So is 0, 0 has the same number, so x1, x2 is equal to x. So we can say that 0, 0 does indeed belong in V. Then I will check for linear combination straight away. So I will say alpha times, let's say I define V1 and V2. So I take a V1 equals some A, and then V2 equals some B. They both lie in the set of elements V. And now I want to see if V3 equals alpha A plus beta B also lies in V. How do we do that? We say alpha times A, this is V1 and V2. So A plus beta times B. This becomes alpha A plus beta B, alpha A plus beta B. Again, x1, the two elements are equal, so I know this belongs to the subset V. And because this belongs to the subset V, I can say that V is a subspace. In R2. So that is our basic idea. Even if we didn't simplify it, we could have kept it in this format and checked the whole thing normally. But we know how to do it. We know first we want to check for the 0th element. If that didn't exist, we'll stop right here at the first check and we'll say that V is not a subspace, but because the zero element checks out, we go on to look at the linear combination property. Now, what helps to visualize this is you can basically say, let's say when you're in R2, you can think of it as a point in the xy plane. So let's try and see what that becomes in Julia. So we'll go here, and as you would imagine, let's say your x goes from -10 to 10, and then your f, which was your v vector, we said is the set of elements x and x. So I define an f which has the elements x stacked in row with x, and then I plot it out, and that becomes a line. And we can see that the line passes through the origin, and we also saw that it satisfies the property of linear, is closed under linear combinations, so you can say that the given set V was indeed a subspace. If that's clear, we're going to move on to an example in 3D and try and visualize that. Yeah? Okay. So what does that look like in R3? So if V is a subset in R3 and V is given as AX followed by BY and then AX plus BY plus C, for this to be a subspace, intuitively from our, and we have to find conditions so that this is a subspace. So for the first check, I will see if 0, 0, 0 belong in V. So does 0, 0, 0 belong in V? Can I get, if I put the first element 0, then A can be anything, and X is 0, Y is 0, and then the third element becomes C. For this to be equal to the 0 element, I get condition on C equals 0. So I redefine my set V as AX, BY, and AX plus BY, such that X and Y are in the set of real numbers. Now this could or could not be a subspace. To do that, we still need to check the property of closed under linear combination. So for check 2, I want to see if alpha 1 V1 plus alpha 2 V2 lie in the set V. So let's define V1 and V2. So we have V1 is going to be, it's an element in V, so it is AX1, BY1, and AX1 plus BY1. And then V2, so it's AX2, BY2, and AX2 plus BY2. They're both elements of V, and the linear combination of them should also ideally be the element of V, and if that's true, then we can say that V is a subspace. So let's check that. Let's multiply alpha 1 V1 plus beta V2. That becomes A times alpha times x1 plus beta times A times x2. This becomes A times alpha times y1 plus beta times, this is B. Oh, that was A. This is B. And beta times B times y2. And this becomes alpha AX1 plus alpha BY1 plus beta AX2 plus beta BY2. Does this look like an element of V? Well, it'll be easier to see if we get the A terms out. So this becomes A times alpha x1 plus beta x2, B times alpha y1 plus beta y2, and this becomes A times alpha x1 plus beta y1 plus B times alpha y1 plus beta y2. Beta, yeah, and this should be x2, my bad. This is x2. So if I call an element x3 equals alpha x1 plus beta x2, and y3 an element alpha y1 plus beta y2, then this vector v3 is basically a x3, b y3, and ax3 plus by3. How do I know if x3 and y3 are still real? We know that the set of vectors is defined by real numbers is a subspace in itself. So any linear combination of a real number is always a real number, which we can also think intuitively, like if you multiply a real number to another real number and then you add a bunch of them together, they will always still be a real number. There's no way you can get an imaginary number like that. So then x3 and y3 are real numbers, and by that logic, we can show that v3 indeed belongs in V. So our conclusion is again that V is a subspace in R3. we got the condition C equals 0 out in the beginning. Otherwise, that would have messed things up. But it's an easy test where we just look at the 0 vector and we want to make sure that it is in our subspace. If this is clear and there's no questions here, we can look at what this means geometrically. So if you try to plot a point like a subspace like this in Julia, what you'd want to do is, so what this is doing is basically getting a set of vectors x and y such that I have something like -1, and then -1, and then the increment in y. I think it would help if I print out what x is. So then x goes from -1, -0.50, 0.51, and then y will also go from, it's basically defining like a grid in x and y. So then y is -1, -1, and then x was the different, actually, let's see, I can probably print out the xy grid. That'll be easier, yeah. So these are all the different points in xy. So -1, -1, -0.5, -1, 0, -1. Basically defining different points in an xy plane. Now that we have that, I want to look at, let's say A and B have arbitrary values between -5 and 5, and C you have to set to 0. So what does that subspace look like? So then that subspace basically looks like a plane passing through the origin right here. And it's formed, like each point in this 3D space has been formed by a linear combination of your vector elements, which are given by ax, by, and the z is given by ax plus by plus c, in this case, which is 0. And you get a plane which we can manipulate. So right now, this is for a equals 0.8 and b equals 0.4. I can change my a and see what happens. I think I'll have to run it again. Let's see. Let's try to run it again. Yeah, that gives it for the 0, 0, but that'll be fine. So then, for different values of b, you can still see that it's a plane, and it'll always pass through the origin. It's a little hard to see, but the origin is always this center point right here. And no matter what value of a you choose, you'll still get a subspace in R3. We can play around with this. And it probably won't work in the Illumi desk, so I'll change it to where you'll have to change manually the values of A and B, but the idea is the same. You just wouldn't get the sliders. We're working on it, but we don't have the sliders in the Illumi desk yet. So that's basically what a subspace in R3 will look like. Hopefully that was clear. If you have questions, put it in the chat, or you can just say them out loud. So now that we understand subspaces, we can move on to what we've talked about in lecture about null spaces and range of a matrix. So let's look at what the null space of A will be. The null space of A is just the set of all vectors x in Rm such that Ax equals the 0 vector. So if we know for a fact that all columns of A are linearly independent, then this null space of A should just be the trivial 0 vector. And we'll look at an example of that. But that is how we define the null space of A. And then the opposite of that, the range of A will be all linear combinations of columns of A. So like this A times X will basically be x1 times the first column of A plus x2 times the second column of A to xm times the mth column of A. All linear combinations of columns of A are called the range of A, and later we define that to be the column span. But the two are comparable. Just for all x in Rm, when you apply A to it, all such values, all such vectors saved as y are called the range of A. Using that definition, then we're working out some questions in homework. So we can look at an example. I think this is from the book. So let's try to find the null space of A, where A is this given matrix. So when we're trying to find the null space of A, it is equal to x in our number of columns of A, which is 3, such that A of x equals the 0 vector, just in this case 3 cross 1. So I'm going to assume my x is some x1, x2, x3, and then A times x becomes 1, 2, 3 times 0, 1, 2 times 0, 0, 1 times x1, x2, x3, and I put that equal to the 0 vector, which gives me 3 equations and 3 unknowns. And because it's an upper triangular matrix, I can easily solve it using back substitution. And if you try and do that, you'll find that x3 equals 0, and then x2 plus 2x3 equals 0, so x2 equals 0, and then x1 plus 2x2 plus 3x3 equals 0. By that logic, you'll get x3 also equals 0. And so then the null space of A becomes just the 0 vector. Which basically is trying to say that when this is true, this also means that columns of A are linearly independent. Now, let's try to find the range of A. So we define range of A is y in Rm, which is in our case R3, such that y equals A times x, where x is also, in our case, in R3. So then y is defined by some, let's define x first actually. So let's say my x is some alpha 1, alpha 2, alpha 3. So then my y is alpha 1, first column of A1, 1, 0, 0, plus alpha 2 times 2, 1, 0, plus alpha 3 times 3, 2, 1. And because we know the columns of A are linearly independent, this basically becomes our range y given by the linear combination of columns of A such that alpha 1, alpha 2, alpha 3 are real numbers, or x is in R3. And that becomes the range of our matrix A. Let's try and do that for a matrix that doesn't have all linearly independent columns. So I know, just looking at it, that the columns of A, because m is greater than n, will not be all linearly independent. Let's try to work out the null space of this A matrix. So here, the null space of A is the set of x's in R3 such that A of x equals, x in R2 such that A of x, that was correct, m is 3. A of x equals 0, 0. So then that means I'm trying to find my x such that 1, 2, 3, 0, 2, 2 times x1, x2 equals 0, 0. If you try and solve it, you get, I've missed an x3 in there. And then this becomes x1 plus 2x2 plus 3x3 and 2 times x2 plus 2 times x3 equals 0, 0. Try to solve it. Naively, just looking at it, I can tell like the third column is the combination of the first two columns. So we can either say, let's try and choose and solve it the naive way. Let's say x3 equals 0, and then x2 equals 0, and then, we want to get x1, x2, and x3 such that these two equations satisfy. And that will be for all elements in I'm gonna choose, if I choose x1 to be some A, then my equations become to be 0. My equations become blanking out. Okay, let's try and do this. We know that 3, 2 is a linear combination. So we can safely eliminate the last column. So we know that the null space is not 0. We try to find that. So I take x1 equals some value, say alpha, and then this becomes I subtract 2 from 1. This is a2. And I get, let's leave it x1 actually. And then I do equation 2 minus equation 1. Or 1 minus 2 actually, it would be easier. 1 minus 2. And this becomes x1 plus x3 equals 0. I get x1 equals minus x3. So if I take this to be alpha and x2 to be beta, my solutions are alpha minus alpha and some beta. And whenever I do that, it should satisfy the condition. So alpha plus 3, yeah. And then we add the 2, and then we also get x1. Replace that in there. Replace in 2, and you get x2 also equals minus x3. Then your null space is simply alpha times 1, 1 minus 1, which makes sense. And then we say the null space of A is the set alpha 1, 1 minus 1, such that alpha belongs to R. And the range is simply the set defined by alpha. So if I take x is alpha 1, alpha 2, alpha 3 like we did before, so the first column is 1, 0 plus alpha 2. Second column is 2, 2 plus alpha 3. Third column is 3 given alpha 1, alpha 2, alpha 3. R and R. We also know that this vector is a linear combination of these two vectors. So we can eliminate alpha 3, and so the range of A becomes just the set alpha 1 plus alpha 2, where alpha 1 and alpha 2 are real numbers. So this is basically from the definitions, and where we'll use this is basically when we're trying to define the nullity and the dimension, the rank of the matrix A, and that formulation just helps us answer a lot of questions when we're trying to solve AX equals B. And if you can say, like when we looked at the null space of A, if the null space of A only had the 0 element, we said that columns of A were linearly independent, which means if I had an equation AX equals B, then as long as B was in the column span of A, there would be a solution, and the solution will be unique. To make it more clear, for a system of linear equations, we expand on what we call a column span. So the span of any set is basically, so let's say there's a set V, V1, V2 to Vn, then the span of V is the linear combination of all the elements in V, which is alpha 1 V1 plus alpha 2 V2 to alpha n Vn, where alpha to alpha n can be any number in the set of real numbers. So when we say we want to define the span of a column for a matrix, the column span of a matrix becomes the span of the set that contains all the columns of that matrix. And we use that again in the formulation for our solution for linear equations. Another thing that we can define here is the rank and the nullity of any matrix. So the rank of any matrix is the dimension of the column span of A, and the dimension means the number of basis elements of the column span of A, or the number of linearly independent elements in the column span of A. And if you think about it, the number of linearly independent columns in a span of any set of vectors is the same as saying the number of linearly independent vectors in that set. So so the rank of A basically is the number of linearly independent columns of A, which we can also write as the dimension of the column span. Similarly, the nullity of A is the number of linearly independent vectors that you can write in the null space of A. So if the null space of A is just the 0 element, then the dimension of the null space is 0, and then the nullity of A is 0, which means that the nullity of a matrix that has all linearly independent columns is always 0. Where we use this? Well, we use this in we've defined something called a rank nullity theorem, which says that for any matrix A, which is M cross N, the rank of A plus the nullity of A should be equal to the number of columns. So given any matrix A, if we know how to find the column span, we know how to find the null space, and we know how to count the number of linearly independent vectors in any set, then we have everything we need to prove the rank nullity theorem for any matrix A. So if we have the same A matrix from before, which we just did, we found the null space of A to be the set of elements right here. Alpha times 1, 1, minus 1, such that alpha lies in the set of real numbers. So this basically means that the nullity of A will be the number of linearly independent columns in this set that we've just defined. And because this set is made up of linear combinations of just this one vector, then the number of linearly independent vectors in this set is basically just this one vector. So we can say that the nullity of A is equal to 1. Similarly, we found the range of A to be y such that y equals alpha 1 times 1, 0 plus alpha 2 times 2, 2, such that alpha 1 and alpha 2 are real numbers. So from here, you can tell that all elements y in the range of A can be defined as linear combinations of just these two vectors that are linearly independent, which means that the dimension of the range of A, which is also the column span of A, column span of A, how do we know that? Because column span of A is basically alpha 1 A1 plus alpha 2 second column plus alpha 3 third column. Again, we can say because the third column is a linear combination of the first and the second column, we eliminate alpha 3, and then the range and the column span are actually comparable. And then we look at the dimension of it, and like we discussed, there's only two linearly independent vectors in that set of vectors that we've defined. So the rank of A is equal to 2. Now, what is the number of columns in A? The number of columns in A is 3, so the rank nullity theorem becomes M is equal to 3, which is equal to the nullity of A plus the rank of A, hence proved. Now this is in general true, but we've just proved it for the one example that we've had. And that is clear. We can move on. We can talk about the bases of any subspace. In fact, before we move on, we can look at what it means when we talk about all these spans in Julia. So null space and range. This is the first example that we had in here. So all columns of A were linearly independent, and we can basically say that the range of A is alpha 1, 1, 0, 0, alpha 2, and alpha 3. It has three linearly independent vectors, and as we discussed in class, it will be, so if you're working in R3 and you found three linearly independent vectors, we can say that the three linearly independent vectors that we found are the bases of R3. I think it'll be easier if we talk about this after we've gone over what bases mean. So, talked about subspaces, we talked about rank, we talked about nullity, talked about how to find the null spaces. The next thing is, if we have a subspace and we know how to find if a subset is a subspace, then how do we find a basis for that subspace? So any set of elements V1 to Vk are bases for any subspace V if they satisfy these two properties. So the set V1 to Vk, which we are trying to see if it's a basis for V, if that set, first of all, is linearly independent, and the linear combination of that set can give me all elements in V. So the span of the set V1 to Vk is V, which basically means any element in V can be written as alpha 1 V1 plus alpha 2 V2 to alpha k Vk. If we can prove this, and we can prove that all of them are linearly independent, then the set that we have is indeed a basis for subspace V. And the dimension of V is then the number of basis vectors that you can find. So in this case, it went on till k. There are k vectors in my set of basis vectors. So my dimension of V is k. Let's try and see how we find the basis of the subspace. So given an A matrix, I define a subspace S that is in the column span of A. So basically, what that means is any element in S is a set such that any element in S is given by alpha 1, the first column of A, plus alpha 2, the second column of A, plus alpha 3, the third column of A. So for this set, and also they're all real numbers. So alpha 1, alpha 2, alpha 3 are all real numbers. Let me actually decrease the size of this thing. It's too big. Yeah. So that's what we mean when we say that we've described a subspace from a column span. How do we know it's a subspace? Well, first of all, we know that all column spans and ranges are actually subspaces. So we don't actually need to check if it's a subspace, but the proof of that statement is in the book. Next thing we need to see is I want to find a set of vectors V such that V1, V2, V3, and so on can define the set S. So the span of V is the set S. So let's do the second property first. I want to find, let's say I choose my V to be all columns of A. So the first column of A, the second column of A, and the third column of A is my set of vectors V. Now by definition, the column span of A is basically the span of V. So the span of V is equal to the column span of A by definition, because V is just a collection of all the columns of A, which is the definition of what a column span is. Next thing is, I want the set to be linearly independent. So from here, I know that the third column can be written as the first column plus the second column. So we can eliminate the third column and not lose anything because it's a linearly dependent column. So I redefine my V to just have the first and the second column of A, and then this becomes the basis of S, which is the column span of A. And why do we know that it will still have the same, it will still give us all elements in the column span of A, is because we've only deleted the linearly dependent column. So the span is still the same. If that's clear, we'll move on.
Should we phrase that question for number one? So then we would just say like the first two columns are the answers?
Yeah, because the third column we found was a linear combination of the first and the second.
Mm-hmm.
So so then this can be written as a linear combination of these two. So I eliminated from the set, and I only have these two in there. So they satisfy both these properties. They say that the first two are linearly independent. So this is satisfied. And the span of the two of them will give me all the elements in the column span, because any of the elements that came from the third column are already a linear combination of these two columns.
Okay, that makes sense. Thank you.
No problem. So that satisfies both our properties, and so we can say that that is the set of basis vectors. And so the dimension of S is the number of basis vectors, which is 2 in this case. Similarly, let's try and solve this one. So we opened this up as a square in the first problem that we solved. So this one right here, the set V that we defined, we called it x1 minus x2 whole square, and we find out the set V is basically the set where both x1 and x2 are equal to any number x. So what would be the bases of a vector, of a set of vectors defined in V? Well, let's write that down here. We said we simplified it to be V such that V is an element x given x belongs in R. Now, this can be written as alpha times 1, 1, where alpha belongs to the set of real numbers. So then, by this, we're saying that any element in V can be written as a linear combination of this vector 1, 1. And by that logic, we can say that if I take the set of vectors V to be just the set 1, 1, then the span of V becomes alpha times 1, 1, which is curly brackets, which is equal to V, and also there's only one vector in V which is linearly independent. So we satisfy both properties that we need to be a basis. So we say that this small v is a basis for the capital V, the set V. And the dimension of V is 1. If that's clear, we'll do one more example, because I feel like basis is a little bit of a harder concept to grasp, but it's also important. Yeah? So then by the same logic, let's say I defined a vector A, and then my set S is the span of A. So then S is just alpha times 1, 2, 3, where alpha is a real number. So if I take the set of bases vectors V to just be 1, 2, 3, I will see that the span of V is the linear combination of the one element that is in V, which is alpha times 1, 2, 3. And alpha is a real number. What is this? This is exactly S, and also elements in V are linearly independent because there's only one element, so it has to be independent, and it's not a zero element. If it was zero, then it wouldn't be. So it satisfies both properties, so then V equals just this one element is a basis for the set S. And since there's only one element in V, we can say that the dimension of S is 1. That's basically different ways that people will define subspaces, and then have you come up with a set of basis vectors. The thing to remember is basically just that you want to write down your set that's given to you. So if you're given a subspace, write down that subspace. So if I say span of A, write it down, what it means as a set. Then you want to look at if you can write it down as a linear combination of a set of vectors. In this case, it was easy because it was a span, so I can already see that I can write it. It's already a linear combination of this set, this element, 1, 2, 3. So from there, you see that this is in itself the span of this V element is equal to S, and then from there you want to check if all the elements in V are linearly independent. If they're not, then remove the element that is dependent, and you'll still have the same span, and then that will be your basis vector. Kind of like what we did here. We had alpha 1, alpha 2, alpha 3, but then we looked at the third column and we said that's dependent on the first and the second column, and so we can remove that from our set of basis vector.
So, Triby, do we go with number 3 and number 1 about like the same way?
Yep. So
you just did more explaining in number 1, correct?
Yeah. So it's the same method. What you want to do is step 1, write down the set S as a set of elements. Then you want to write down the different elements in S as a linear combination of some vectors. Then you want to define a set small v, which then picks out all these vectors to vk. And then, so this is step 1. Step 2 is define the set of basis vectors. And then step 3 is remove all Vm that are linearly dependent. And that becomes your set of basis vectors.
Okay, that makes so much sense. Thanks so much. You're also going to upload this right after you're done, correct?
Yep. Yeah, I'll clean it up a little bit and then I'll upload it.
Okay, thanks so much.
Yeah. So now that we understand how to find a set of basis vectors, we have another process called Gram-Schmidt, and what we basically want out of Gram-Schmidt is we want a set of orthogonal basis vectors, and orthogonal basically means that the dot product. So when I say V1 is orthogonal to V2, that means that the dot product of V1 and V2 is 0, also written as V1 dot V2 is 0, which is the same as saying V1 transpose V2 is the 0 element, where V1 and V2 are in Rm. They're column vectors. How do we do that? So given a set of linearly independent vectors, that's important. So U1, U2, Um, they're all linearly independent. You can get a set of orthogonal vectors, V1, V2, Vm, such that V1 is orthogonal to V2, V2 is orthogonal to V3. All of them are mutually orthogonal. And the way to do that is using Gram-Schmidt. the first element is equal to u1, the second element is given like this, and we can work it out in this example that we can take, and let's try to do that. So then this becomes, if u1, u2, u3 is these set of vectors, step 1, you get v1 equals u1, and you're done. Then step 2, we find v2 such that v2 is orthogonal to v1. How do you do that? You say v2 is u2 minus, let's use the formula right here. I'm not going to write it down. So it's u2 is 0, 1, 1, minus the dot product of u2 and v1, which is u1. So the dot product of this is basically 0, 1, 1, that is u2 transpose, times v1, which is u1, which is 1, 0, 0, divided by v1 dot v1, which is basically the sum of the square of all elements of v1. So that is, for our case, like 1 times 1, 1 squared plus 0 squared plus 0 squared, which becomes 1. So times 1 times v1, which is this element 1, 0, 0. This becomes 0, 1, 1, minus this product will become 0. 0 times 1 times 1, 0, 0, and that's basically just equal to u2. Finally, the third element is u3, which is 2, 1, 3, minus, where'd it go? So u3 minus u3 dot v1. So that becomes 2, 1, 3 dot v1, which is 1, 0, 0, divided by v1 dot v1, which we found to be 1, times v1, which is 1, 0, 0, minus u3 times v2, and then v2 is 0, 1, 1, times divided by the square of all elements in v2, which is 1 squared plus 1 squared, which is 2, and then this becomes 1 by 2 times v1 times v2, sorry. So that's 0, 1, 1. This becomes u3 minus this element is 2 times 1. So this is 2, 0, 0, minus this is 3 plus 1 is 4, 4 by 2 is 2, so 0, 2, 2. And this becomes 0, minus 1, 1. Now we can check and this V1 is same as U1 is 1, 0, 0. Is V1 dot V2 equals 0? So 1 times 0, 0 times 1, 0 times 1 is 0. Is V2 times V3 equals 0? So 0, 0, this is 1 times minus 1, and then 1 times 1, and that's 0. So we can check that V1 is orthogonal to V2, V2 is orthogonal to V3, and then V1 is orthogonal to V3. Which is what Gram-Schmidt promised. So we have a set of orthogonal basis vector. Next thing is, where do we use your Gram-Schmidt? Well, we use it in Qr factorization, which we use to solve the system of linear equations by decomposing any matrix A as A equals Q times R, where Q is an orthogonal matrix, which means that Q times Q transpose times Q is the identity matrix. The way to do that is we build Q such that all the columns of Q are given from the Gram-Schmidt process, further by normalizing them. So each column of Q is orthonormal, and from that we can also find out R. So let's say you were given a matrix A which had linearly independent columns. How would you find the Qr factorization? Well, you'll take A and you will create a set of vectors U1 to UM, which are basically U1 is the first column of A, and then U2 is the second column of A, and so on. Then from this set of vectors, you will do the Gram-Schmidt process and you'll get a set of orthogonal vectors. So V1, V2 to Vm are orthogonal. And then to make them orthonormal, you will normalize, so divide them by their norm, and you get this new set of vectors, which is V1 by norm of V1, V2 by norm of V2. And you stack them up and you get the matrix Q. And Q will satisfy this property always because of the way that we built it. Then when we're trying to find A equals Q times R, we can find R because Q transpose times Q is I. That means if I multiply both sides by Q transpose, so A equals QR, multiply both sides by Q transpose, and you get Q transpose Q times R. This is the identity, and anything multiplied with the identity is just the same matrix. So Q transpose A is equal to R, which is how we find the R matrix right here. So let's say you were given this matrix A and you were asked to find out the Qr factorization. To make it easier, this is basically the different columns that we just found out. I stacked them up and I made the matrix A. So basically, this first step is done for us because that's how we define the A matrix. The next thing is you want to find a Q. So we also have V1, V2, V3 that we found from the previous example. And let's write that down. So v1 and u1 were equal, so this was 1, 0, 0. This was 0, 1, 1, and this we found to be 0, minus 1, 1. So we have our set of orthogonal vectors. To find out Q, we will normalize our vectors. So then Q becomes v1 divided by the norm of v1. Norm of v1 is 1. Then the next column is given by 0, 1, 1, v2, and the norm of v2 is 1 upon under root 1 squared plus 1 squared, so root 2. And then the third column is 0, minus 1, 1. And then again, the norm is root 2. So then our Q matrix becomes 1, 0, 0, 1, 1 by root 2, 1 by root 2, 0, minus 1 by root 2, and 1 by root 2. Now that we have our Q matrix, how do we get R? Well, R is Q transpose times A. So R is Q transpose, so let's transpose our Q. That becomes, and then 1, 1 by root 2, 1 by root 2, then 0, minus 1 by root 2, 1 by root 2, times A matrix, which is 1, 0, 0, 0, 1, 1, 2, 1, 3. Try to solve it. You'll get something like this element is 1, this element is 0, this element is 2, and this is 1, this is 2 by root 2. Oh, that one's too big. But you can do it in Julia, and it's probably an easy solution. In fact, we can look at it. Put this one example up for range and null space. We ran out of time, but it should be intuitive, the plot. So, given A, I wrote down what we found our Q to be. And I was going to go over how to get R without doing it, but we can go over it some other time. So if we're just looking at this, I'm going to copy the Q. We have the A matrix, we found our Q, and then R is Q transpose times A. Then let's do Q times R, and your Q times R looks exactly what our A was. And our A was 1, 0, 0, 0, 1, 1, 2, 1, 3, which is basically what we have here. Which means our solution was actually correct.